Hi, welcome back to 345 Delta Foxtrot. My name is David Forgerson. I've been making a series of videos about riveting. In the last 4, I've been measuring the strength of rivets under various circumstances. And this video is going to be a continuation of that. This video is about blind rivets, and I suspect this is going to be a fairly long video, and I apologize for that, but I want to just get it out of the way. I thought about breaking it up into 2 videos, but you can do the same thing. If you get tired of watching it, just hit pause and come back and finish watching it some other time. Okay, experiment number 5 is fairly simple. We're just going to find out how strong blind rivets are by measuring the strength of an LP 4-3 and a CS 4-4. The aluminum for this experiment is the normal Van Skin aluminum, which is thin. It's only about 16 thousandths thick, and it's a 2024-T3 alloy. It's the same aluminum I've been using in the last several experiments. Okay, these are the rivets that I'll be testing. And the Van's part number for the first one is LP 4-3, and I have no idea where they got that or why they use a different part number. But as far as I can tell, the manufacturer of these rivets is Expt, G-E-S-I-P-A. I'm not sure how you pronounce that. And their part number is GSMD 41-43 APG, and this is a multi-grip rivet. That's where the 41-43 comes from. The 4 means that it has a diameter of 4/32 or 1/8 of an inch. The 1 in the 41 means that it has a maximum grip of a 1/16 of an inch, and the 3 means that it has a maximum grip of 3/16 of an inch. So since this is a 41-43, it means that it has a grip basically from 0 to 3/16 of an inch. And the grip range is shown in the table. 1, 2, 3, it's in column number 5. And it's from 39 thousandths to 197 thousandths. 39 thousandths is pretty small. 2 16 thousandths skins would be 32 thousandths, and that's about as thin as you can go. So the LP 4-3 is a dome head rivet. The body material is aluminum, and the mandrel is steel. And according to the manufacturer, the shear strength is 162 and the tensile strength is 236 pounds. Now, that I'm sure is for thick aluminum, basically the optimum case. And I'm going to be measuring the tensile strength for thin aluminum. The CS 4-4 is similar part number and manufacturer, similar grip range. The real difference here is that it has a countersunk head, and again, it's an aluminum body rivet. And the manufacturer's shear strength is 155 pounds, and the tensile strength is 205 pounds. And here's the results of my strength measurement. The LP 4-3 with the dome head was pretty strong. it was stronger than most of the solid rivets that I've measured. It was, of course, this is basically a number 4, an 1/8 inch rivet, and the solid rivets were all 3/32 or number 3 rivets. The strength was 152 pounds, and the factory head came out just fine. And the dome head, it was the shop head part that failed. And for the CS4-4 with the countersunk head, it did very poorly. It had a strength of 76 pounds, which is basically the lowest I've measured. I'd have to go back and check my videos or my notes to make sure of that, but I believe that it's the lowest value that I've measured. And in this case, it's the factory head that failed. The factory head just pulled right through the thin aluminum and fairly easily. Here's a picture after they failed. The one on the left is the LP4-3 with the dome head, and the top row is the factory head and the bottom row is the shop head. And as you can see, the LP4-3, it's the shop head that failed and pulled through the hole, whereas in the CS4-4, it was the factory head that failed and pulled through the hole. Okay, what did we learn from experiment number 5? Well, for thin aluminum, dome head rivets seem to do quite well. It's because they have a fairly large head, and it keeps the factory head from pulling through the hole. And also they have a fairly large shop head. As you probably saw in the previous picture, the shop head on blind rivets is, it's a fair size. The mandrel pulls a pretty big chunk of metal up, against the skin and whatever, the piece of metal that you're riveting. And countersunk blind rivets, or at least the CS4-4, was pretty weak. It did fairly poorly. And the countersunk head just pulled right through the metal. Okay, since we're talking about blind rivets, we're done talking about my experiment and the values that I measured. Let's just talk about blind rivets in general. The first thing probably I should mention is there's different words for blind rivets. The 3 common ones are blind rivets, pulled rivets, and pop rivets. Pop rivets, that's the name of a manufacturer. And Pop was actually bought by Stanley Engineered Fasteners. I believe that's the name of the company. It's Stanley something like that. Those Stanley bought Pop, but they're still selling the Pop line of rivets as Pop rivets. But it's kind of a generic name, like Kleenex. Everybody just thinks of it as a Kleenex, but it's actually, Kleenex is a brand of tissue. And then pulled rivet, I kind of like that name because I think it's fairly descriptive. Maybe, better, more descriptive than blind rivet. But the preferred terminology seems to be blind rivet. And there is no standard notation for blind rivets, unfortunately. I wish that the manufacturers would get together and come up with a standard notation, but they don't seem to have done that. This is Cherry's notation, and it's a fairly good notation, and even though other manufacturers don't necessarily follow it, they tend to do something kind of similar, so it's worth going over. The first letter is the rivet material, and the most common one is probably B, at least in the aircraft industry, which is 5056 aluminum. C is stainless steel. That's also fairly common. Then there are, other materials like Monel and steel and copper. And if actually not the first letter, the first three letters are CR3, that indicates that it's a Cherry Max rivet. And we'll talk more about Cherry Max rivets in a later slide. The second letter is the mandrel material, and I believe that steel is the most common there. Now for stainless steel rivets, you would almost certainly have a stainless steel mandrel. Now for aluminum rivets, you would probably still have a steel mandrel, although you can buy aluminum rivets with an aluminum mandrel. I'm not sure what the advantage of an aluminum mandrel would be, since the mandrel, well, that's not quite true. For the cheap rivets, which are often referred to as the Type N rivets, the mandrel pulls through and gets thrown away. Now I believe that for like Q type rivets and Cherry Max type rivets, a piece of the mandrel ends up staying in the rivet, and that's what gives it its strength. And so in a case like that, there would be a significant difference between aluminum and steel, but you would probably still want steel. But if you wanted an all aluminum rivet, I suppose that would be a possibility. The third letter is the head style, and the CS4-4 was a dome head or a protruding head. Cherry uses P, and they call it protruding, but it's the same as a dome head. L means a large head rivet, and C means a flush or a countersink rivet head. And the fourth letter, if there is one, if there is not one, then it means it's a Type N rivet. And if there is one, it's probably a Q, and that means it's a Type Q rivet. And Type N rivets are the cheap ones, and Type Q rivets are stronger, and they're just called Type Q rivets. The first number is the diameter in 32nds of an inch, so it's usually 4, at least for the rivets that we use. And that means that it's an 1/8 inch rivet. And the second number is the maximum grip length, or in 1/16 of an inch, and that varies from 1 to probably 5 or 6. I don't know how high it goes. And an example would be a BSPQ-42. That would be an aluminum body with a steel mandrel, a protruding head or a dome head. It would be a Type Q rivet, and it would be an 1/8 inch rivet, 4/32, and the maximum grip would be 2/16 or 1/8 of an inch. Okay, I've already briefly mentioned this. The cheap ones are the Type N rivets. the type Q rivets are a little stronger, and the strongest ones are the Cherry Max rivets. And the strengths are given here in this table. A type N rivet is 170 shear and 220 tensile. A Q type rivet is roughly twice that, 350 and 325. Twice that for shear strength and 1.5 times that for tensile strength. And the Cherry Max rivets are the strongest, and they have a shear strength of 664 pounds and a tensile strength of 285 pounds. And my understanding is that you can use a Cherry Max rivet to replace any solid rivet. That Cherry Max rivets are actually stronger than solid rivets. So they're used when you've worked yourself into a problem spot and there's no way to get a bucking bar in behind the rivet or get a squeezer in. And so you just use a Cherry Max rivet. Now, the type N rivets are typically like 10 cents a piece on that range. The type Q rivets are like a quarter a piece or 30 cents or somewhere in that range. And the Cherry Max rivets are typically about $1 a piece. So, you might be thinking, well, why not just use Cherry Max rivets everywhere? Well, that's the reason. It would get pretty expensive. Okay, I'm going to talk about some different rivet types, or a lot of different rivet types. And the screen is going to get pretty crowded with numbers. You do not have to pause the video and write down all these numbers. I made a spreadsheet. The spreadsheet is in this link right here, and I'll put the link in the description. And so you can always just click on that link and read the numbers at your convenience. Okay, this is all the rivets that Van sells, with the exception of Cherry Max rivets. Cherry Max rivets, like I said, are not used as a regular part of a kit. They're just used kind of in emergency cases. We're not going to go over all of these. Like I said, you can always just look at my spreadsheet. Okay, this is where those rivets are used in which RV kits. And as you can see, there's, looks like 4 that are not used in any kit at all. So let's throw them out. Okay, here's the rivets that are actually used in one of the RV kits. And okay, now I've narrowed it down to just the rivets used in an RV10, because that's what I'm building. You may be more interested in some of the other rivets, and in that case, look at my spreadsheet, download my spreadsheet, and figure out what rivets that you're most interested in. Okay, this is the LP4-3. This is the one that I measured the strength of, and it was, I believe, 170 pounds. Oh, no, I'm sorry, it was 152 pounds. And As I mentioned before, it's a multi-grip rivet. Has a dome head. It's used in many different places in the kit. And it's also the rivet that's used for the RV12 for riveting all the skins. The RV12 does not use solid rivets like all the other RVs. And because of that, because it's used so extensively in an RV12, it's the only rivet that's sold by vans in boxes of 10,000. So I believe that in quantities of 1, an LP4-3 is 17 cents a piece. In quantities of 10,000, that drops down to 9 cents a piece. And so, you know, there would be an expense to using all LP4-3 rivets, you know, to rivet the skins of your plane, but it wouldn't be that bad. And you probably wouldn't need to buy a lot of the tools that are required for solid rivets. So it'd probably be a wash. Another plane that uses this rivet is the Sling TSI. And it's kind of an interesting comparison to the RV10. The Sling TSI uses these blind rivets with the dome heads, so its structural strength is probably as good as the RV10. As we saw, you know, I measured 152 pounds, and I typically measure 125 to 130 pounds for a solid rivet. So the only real disadvantage to the blind rivet is cosmetic. The plane is not going to look as nice with nice smooth skins when it's done, but after it's painted, I'm not sure exactly how much that's going to matter. And the other thing is air resistance. And the RV10 is a slightly faster plane than the Sling TSI. So maybe 20 miles an hour, something like that. I don't know the exact number. But the RV10 also has a bigger engine and uses more fuel per hour than the Sling. So I suspect that the rivets have very little, if anything, to do with the difference in speed. It's almost all due to the fact that the engines are different in the two different planes. So one big advantage of using the blind rivets in something like Sling TSI is it reduces the build time, probably by 500 hours. So kind of depends a little bit on how much your time is worth to you. Okay, this is the CS4-4, and it's the other one that I measured, and it did particularly poorly. I measured 76 pounds of tensile strength with the thin skins, whereas the manufacturer claims that it's 205 pounds, and it's almost certainly with thick aluminum. The shear strength is 155, which is okay, but it's not nearly as good as a solid rivet. I don't have too much else to say about this. It has a countersunk head, and it's used in many different places in RV10. Okay, these are the CCR 264 SS-3-2, which is a stainless steel rivet, and the MK-319-BS, which is a Monel rivet, I believe. It's possible I got those two backwards, but I don't think so. Pretty sure that the SS stands for stainless steel. Let's see, I'm sorry, it's right here. Yes, the SS is a steel rivet, and the MK is a Monel rivet. Now, these are the only two, what you might call type 3 rivets, rivets with a diameter of about 3/32 of an inch, used in the Vans RV10. And the MK is actually a little bit larger than that. So it's possible you might have to drill a slightly larger hole to get it in and to fit. But it's not all that much larger. It's certainly not as large as a Type 4 rivet. It's not 1/8 of an inch. These rivets are basically used when you can't, as a substitute for a normal Type 3 solid rivet, when you can't get a bucking bar in or a squeezer in. This is the type of rivets that Vans uses instead. Now, I didn't measure the strength of these two. I did measure the CS4-4, which is a larger diameter rivet with a countersunk head. So my guess is that the CS4-4 is actually stronger than either of these. Now, the rivet itself is going to be strong. I mean, one is steel and one is Monel. But they're going to pull through the hole. It's the countersunk head on these rivets that's just going to pull right through the thin aluminum, like it did for the CS4-4, except probably more so. And one other thing to mention about the MK-319VS is that there is an option of using this for riveting part of the elevators, and those rivets are not included in the kit. So I recommend that you go to page 9-12, look at step 2, and your basic option is to use a special bucking bar or to use these blind rivets. And if you opt for the blind rivets, they're not that expensive. I would put them on order so that when you get to that step, you'll have them available and you won't have to wait a week for Vans to ship them. Okay, this is the AD-41-ABS, and it's an aluminum rivet with an aluminum mandrel. It has a dome head, has a small grip. The 1 and the 41 means that it has a maximum grip of a 1/16. The grip is given here. It's 32 to 62 thousandths. And it's used for riveting the two pieces of skin together in the curved part of the rudder. And you bend two pieces of skin around to form basically a semicircle, and then you rivet them together. And so you would be riveting something that's somewhere around 32 thousandths thick. And you want something with a very small grip. Now you might say, why not just use an AD-41H instead? Why do we have both the AD-41 ABS and the AD-41H? Well, it turns out the 41H is a closed head or closed end rivet, and the dash ABS is an open end rivet. And you could still use a 41H. It's just, it'd be a little more expensive, probably a quarter a piece as opposed to 10 cents a piece. But, you know, Vans decided to try and save you $1 and use 8041-ABS rivets. Okay, this is the 80-41H and the 80-42H. And they're both closed-end rivets, aluminum body, steel mandrel, dome head, small grip. In particular, the 41 is a very small grip. And they're used in the fuel tanks where you would not want, you know, a rivet with a hole down the center. Okay, this is the MSP 42. It's a stainless steel rivet, stainless steel mandrel, dome head, and it's used for attaching steel to steel, and in particular things like steel brackets. You know, that's whenever you have steel, it means that it's something in the plane that needs to be strong. And this rivet has a particularly good shear strength and tensile strength. It's 550 pounds shear strength and 700 pounds tensile. So it's a very strong rivet. Okay, this is the SD-42-BSLF, and it's a steel rivet as well. The interesting thing about it is it has a large flange head, and it's used for attaching the air seal fabric in the engine compartment. And you know, you're using it to attach something that's even flimsier than the thin skins that Vans uses. So you want something with a very large head. Otherwise, it won't, you know, have any strength at all with a soft, thin material. Okay, I've already talked about different rivet types a little bit, and this is kind of a repeat. There's the Type N and the Type Q and the Cherry Max rivets, which I already talked about. And they're shown here in rows 1, 2, and 4. And in row 3, we have a Type N stainless steel rivet. And you can see that the stainless steel rivets are actually pretty strong. They're not quite as strong as a Cherry Max in terms of shear strength. In terms of tensile strength, they're actually about twice as strong as a Cherry Max. And they're about a quarter of the cost. So why not, you know, just use stainless steel rivets a lot? Why not use them almost everywhere? The only thing I can think of is, well, if you used a whole lot of them, you might have a weight problem. But I doubt that you'd have to use a huge amount for that to matter much. The only other thing I can think of is galvanic corrosion. When you have dissimilar metals, the metals have a different electrochemical potential, and they can react with each other. This is how thermocouples work, and this is how batteries work. In a battery, you also have an electrolyte, and you get the two dissimilar metals cause a current to flow, and it causes the electrodes, the battery electrodes, to corrode. And it's a well-known problem. It definitely can be a significant problem. In particular, like on an ocean-going boat where there's lots of salt water around to act as the electrolyte, it can be a very major problem. And the other issue here is the LP4-3 and the CS4-4 were multi-grip rivets. And if you're looking to replace them, you're going to have trouble finding a multi-grip option. For example, Cherry Max is not available as a multi-grip option. So you have to buy the individual grip range rivets, you know, the 1/16 grip range, the 2/16 grip range, etc. And so you can't just have one rivet and stick it in and be pretty sure it's going to work. What you have to do is you have to measure the thickness of what you're riveting and select the rivet with the correct grip. And one way to do that is with a grip gauge. And here's an example. Aircraft Spruce sells this grip gauge. It's only $15, but it's pretty simple, and you can make one yourself. It's just a piece of metal that goes through the hole for the rivet and hooks around the back end, and then it's basically a ruler, and it just tells you, has little marks on it. It tells you what grip to use, you know, 1, 2, 3, 4, etc. It seems like you could probably make yourself one of these pretty easily, but then again, it's not all that expensive, unless you have to pay for shipping. So if you're ordering something else from Aircraft Spruce, you might want to consider throwing in a grip gauge. And then I was talking about galvanic corrosion, and this is the table of different metals and their anodic index, or their electrochemical potential. And this is taken from Wikipedia. And you see that aluminum is about minus 0.75, and stainless steel is about minus 0.5. So that's a difference of 0.25. So what does that mean? Is that large, small, average? Well, in Wikipedia, their recommendation for harsh environments is to keep it less than 0.15. So if you were building an ocean-going boat, this would not be acceptable. Well, without some other way to mitigate the problem. And typically, or one thing they do in a boat is they put in a big piece of zinc somewhere, which is a sacrificial anode, and that tends to minimize the problem. But I don't think you'd want to do that in an airplane. And for normal environments, which I interpret to be indoor type environments, they say to keep the anodic potential difference to less than 1/4 of a volt. And for controlled environments where the temperature and the humidity are controlled, then you can go up to 1/2 volt. I have not seen or heard anything about galvanic corrosion as related to airplanes. If you have any information on galvanic corrosion as related to airplanes, please leave a comment. I don't think it's all that much of a problem because Vans does not mention it. They clearly use many steel parts, and most of them are powder coated, powder painted. So that may help to isolate the steel from the aluminum, but you would think they would at least mention it if it's a potential problem. And even things like Cherry Max rivets, even though it has an aluminum body, I believe it has a piece of steel down the center. So again, you have aluminum and steel in contact, and all your nut plates are steel, and those are in contact with aluminum. So if it's a problem, I'd really like to know about it and know about how much of a problem it is. And unfortunately, I don't have any information to give you on this other than what's in this table here on Wikipedia. Okay, one thing that you might be interested in with regard to blind rivets is just their appearance. Solid rivets, in particular the flush ones, have a pretty nice appearance. And if you have mostly countersunk flush rivets, solid rivets, you're going to want to be pretty leery about just using a dome head blind rivet. It's really going to stick out on your airplane, just the cosmetic appearance of the outside of your airplane is going to be a little odd. Now from a distance, maybe it won't show, 100 feet, who cares, maybe, but anyway, this is what they look like. The first one is an LP 4-3, it's the multi-grip rivet, it's the one that I measured the strength of. The next rivet is the AD-42H, which is a closed-end rivet. So you want to look at the back side, which is the bottom picture there for number 2, and you can clearly see that it's different than the others. It's closed. And the next rivet is a BSPS-42, and it's a cheap type-N rivet. It has a 2/16" grip, whereas the LP 4-3 was a multi-grip. So again, the back of the rivet, the shop head is going to be a little bit different than the multi-grip rivet. Now, in terms of like tensile strength, the multi-grip rivet is probably better. It has a big fat shop head. The fourth one is a BSPS-43. So it's very similar to the third one, except the third one has a maximum grip of 2/16, and the fourth one has a maximum grip of 3/16. So you can see on the shop head, it sticks out significantly more. Now, it turns out that this piece of metal was an 1/8" thick, so it's right exactly between a number 42 and a number 43. So which one do you use? I would probably be tempted to use a number 43 in that case, but you can certainly run into problems using a rivet that's too long. In particular, the mandrel can really mess up and not break off correctly. So when they tell you the grip range, try and, you know, use the right one. Don't get careless about it. Then the last one is a Q-type rivet, and you can see that for the first four, there's a very distinct hole right in the center, if you look at the top row of pictures. Whereas for number 5, it's left a piece of the mandrel in the rivet. And I believe that's where it gets its additional strength from. Okay, number 6 is a Q-type rivet with a grip of 2/16, and number 7 is a Q-type rivet with a grip of 3/16. So again, the only difference between 6 and 7 is the grip length, and you can see that in the bottom picture. And number 8 is a stainless steel rivet, just a common type N stainless steel rivet, CCP-43. Then number 9 is a stainless steel type Q rivet. The only difference between 8 and 9 is 8 is type N and 9 is type Q. And again, if you look at the top picture, you can see a part of the mandrel is in number 9, whereas there's just a hole in number 8. And then number 10 is a Cherry Max rivet, and this is a Cherry Max with what they call it a universal head, or a dome head, whatever you want to call it. And again, you can see part of the mandrel is left in the rivet, and you can see that the backside of the rivet is significantly different than the other rivets. It's got a lot of metal in the center to give it strength. Okay, these are some countersunk head rivets. Number 11 is the CS4-4, and it's the one that was particularly weak. And it's just a simple type N rivet. The next rivet is, it's a multi-grip rivet. And the next rivet is a BSC-43. So it has a grip of, a maximum grip of 3/16. And, you can see that the shop head is significantly different between those two. And number 13 is a stainless steel rivet. Again, just a type in inexpensive stainless steel rivet. And the last one is a Cherry Max rivet. And it's very similar to the previous Cherry Max rivet, except it has a flush head. And as you can see on the back side, there's a lot of metal there. That's where it gets its strength. Okay, that's it for this video. I didn't time it, but looks like it was about 30 minutes long. So sorry about that, but like I said, we got the blind rivets out of the way, so we can go on to other things now. If you like these videos, subscribe, give them a thumbs up, or leave a comment. All those things tell the YouTube algorithm to recommend these videos to other people with similar interests. Also, it gives me a little incentive. I kind of appreciate it when somebody subscribes. Now, as always, I put links in the description, and the primary link for this video is going to be the link to my spreadsheet. So that'll be in the description. Okay, that's it. Thanks for watching.